What if everything you have ever seen, every star, every galaxy, every distant smudge of light captured by the most powerful telescopes ever built, represents less than a billionth of what actually exists? The observable universe stretches roughly 93 billion light-years across. It contains an estimated 2 trillion galaxies, each holding hundreds of billions of stars. By any human measure, it is vast beyond comprehension. Yet a growing body of evidence suggests this enormous sphere is only a tiny fraction of something far larger, something we may never directly see. The edge of our cosmic vision is not a wall, it is not a physical barrier. It is a horizon defined by light, time, and the strange behavior of space itself. Beyond it lies a region cosmologists can describe only through mathematics, inference, and careful speculation. Some theories suggest the universe continues for trillions of light-years past what we can detect. Others propose it goes on forever. Still others point towards stranger possibilities entirely, where multiple universes drift like bubbles in an unseen ocean, where physical laws shift from one region to the next, where reality itself takes forms we have no instruments to perceive. This is an investigation into the regions science cannot photograph but can carefully reason about. Using cosmology, particle physics, and the latest data from observatories, we will trace the boundaries of what is known, identify where speculation begins, and examine what may exist beyond the visible cosmos. The journey starts with a single deceptive number, the size of what we can actually see. The observable universe is defined by a specific and somewhat counterintuitive concept. When astronomers describe its size, they are not measuring how far away things are right now. They are measuring how far light has been able to travel since the beginning of time itself. The cosmos, as best as current measurements can determine, came into existence roughly 13.8 billion years ago. From that initial moment, photons began streaming outward, carrying information about whatever they encountered. The farthest light reaching our instruments today started its journey near the beginning of this expansion. That light, ancient and faint, defines the outer shell of what we can perceive. It forms a sphere around Earth, centered on our position, with a radius determined by how long light has had to travel combined with how much space has stretched during that travel. The result is something subtle. If the universe were static, the observable region would simply be 13.8 billion light-years in radius, matching the age of the cosmos. But space itself has been expanding for that entire duration. The regions that emitted the oldest light we receive today have been carried much farther away during the intervening eons. By the time those photons reach our telescopes, their source galaxies have drifted to a present distance of roughly 46 billion light-years. That gives the observable universe a diameter of approximately 93 billion light-years, a sphere whose boundary is not a place but a condition. It is the condition under which information has had enough time to reach us. This boundary is sometimes called the cosmological horizon, or more specifically, the particle horizon. It is not a physical edge that one could approach and touch. It is not a wall, a barrier, or a transition zone where physics changes. It is purely an information limit. Imagine standing in a thick fog where visibility extends only a certain distance in every direction. The fog has no inner wall. The world continues beyond what you can see. You simply cannot perceive what lies past a certain point because the medium between you and that point prevents the signal from arriving clearly. The cosmological horizon works in a similar way, except the limiting medium is the passage of time and the stretching of space itself. What makes this horizon particularly strange is its dependence on the observer. Every point in the universe has its own observable region centered on itself. An astronomer on a planet in a galaxy 10 billion light-years away would have a different observable universe than we do. Their sphere of visibility would overlap with ours in some regions, but would also include vast areas we cannot see, while excluding regions we can. There is no privileged center, no special vantage point. The horizon is a personal feature of each location, defined by where light has had time to reach. This raises an immediate and important question. If our observable universe is just the portion close enough that light has reached us, what about everything else? What about the galaxies whose light has been traveling toward us but has not yet arrived? What about regions so far away that their light may never arrive at all? These are not idle speculations. The mathematics of cosmology indicates that such regions almost certainly exist, and in numbers that dwarf what we can currently see. The cosmic microwave background provides a useful reference point. This faint ancient radiation fills all of space and represents the oldest light in existence. It was released when the universe was only about 380,000 years old, during a period when expanding plasma finally cooled enough to allow photons to travel freely. That radiation, which we detect today as a uniform glow at microwave wavelengths, marks the practical edge of what telescopes can observe directly. Before that moment, the universe was opaque. Light could not propagate. So the cosmic microwave background represents a kind of optical wall, not because there is nothing beyond it, but because the conditions of the early universe blocked the transmission of electromagnetic signals from earlier still. Yet even this microwave radiation, ancient as it is, has a defined source. It came from matter that, at the time of emission, was relatively close to where Earth would eventually form. Due to expansion, that source material is now located near the edge of our observable region. Anything that existed beyond that material at the time of emission has remained beyond our observational reach ever since. The horizon, in other words, was already in place at the dawn of the universe. We have always been looking at a finite portion of a potentially much larger whole. Modern astronomy has worked to push the limits of observation in every available way. The Hubble Space Telescope, the James Webb Space Telescope, the Atacama Large Millimeter Array, and dozens of other instruments operating across the electromagnetic spectrum have refined our view of the early cosmos. Each new generation of telescope reveals fainter, more distant objects, but always within the same fundamental limit. No matter how sensitive the instrument, no matter how precise the technique, the horizon remains fixed by the laws of physics and the history of expansion. We can study the contents of our observable bubble with ever-increasing detail, but we cannot extend the bubble itself by looking harder. There's another subtlety worth examining. The horizon is not static. It changes over cosmic time. In the early universe, when expansion was slower and light had less distance to cover, the observable region was much smaller. As time passes, light from progressively more distant regions reaches us, slowly enlarging the volume we can perceive. In principle, this would suggest the observable universe should keep growing forever as new information arrives from farther away. But in practice, something stranger happens. Because expansion is accelerating, the rate at which space stretches is gradually outpacing the rate at which new information arrives. There is a future horizon called the event horizon of the universe, beyond which we will never receive any signal regardless of how long we wait. Galaxies currently visible to us are slowly drifting across that future horizon, and once they cross it, no further light from them will ever reach our instruments. This creates a kind of cosmic isolation that grows with time. In the distant future, observers in our galaxy will see fewer and fewer distant objects. The night sky, currently dotted with the faint signatures of countless galaxies, will gradually empty. Eventually, only our local group of gravitationally bound galaxies will remain visible. The rest will have receded beyond reach, their light stretched into wavelengths so long they cannot be detected. This future is calculated, not speculated. It follows from the measured acceleration of expansion and the known laws of physics. So the observable universe is not a thing, it is a condition. It is the volume of space from which signals have had time to reach us under the constraints of light speed and cosmic expansion. It is enormous by any human measure, yet entirely defined by limits rather than by content. The actual universe, the thing of which our observable region is just a sample, almost certainly extends far beyond. The question is how far and what it contains, and whether the rules that govern our local cosmos apply elsewhere. To begin answering those questions, we need to look more closely at the most fundamental feature of the universe, the medium that carries everything we can see toward us across vast gulfs of time and distance. We need to examine light itself and the strange, slow, deliberate way it crosses an expanding sea of space. Light is the messenger of cosmology. Almost everything we know about the universe beyond our solar system comes from photons that have traveled across enormous distances to reach our detectors. Yet light, despite its reputation as the fastest thing in existence, is fundamentally limited. Its speed is finite, approximately 300,000 kilometers per second in a vacuum. This number, while staggering by human standards, becomes almost slow when measured against the scale of the cosmos. A photon leaving the surface of the sun takes about 8 minutes to reach Earth. A photon from the nearest star beyond the sun takes more than 4 years. From the center of our own galaxy, light requires around 26,000 years. From the Andromeda Galaxy, our nearest large neighbor, the journey takes 2.5 million years. And from the most distant galaxies ever observed, the journey has lasted more than 13 billion years. This finite speed has a profound consequence. When we look at a distant object, we are not seeing it as it is now. We are seeing it as it was when the light first left its surface. The farther away something is, the further back in time we are looking. Astronomers refer to this as look-back time, and it transforms every telescope into a kind of time machine. Observing a galaxy 10 billion light-years away is identical to observing a galaxy as it appeared 10 billion years ago. We cannot see the present state of distant objects. We can only see their past. This produces a strange and beautiful layering of cosmic history. The night sky is not a snapshot of a single moment. It is a composite image spanning the entire age of the universe. Nearby stars appear as they were just years ago. Distant galaxies appear as they were when the universe was much younger. The cosmic microwave background appears as it was when the universe was only 380,000 years old, a hot plasma cooling into transparency. Every wavelength, every photon, every image is a fossil of a different era. There is no way to bypass this. There is no faster signal, no shortcut. Information cannot travel faster than light, according to every well-tested principle of physics. Whatever exists beyond the reach of light is beyond our ability to perceive, regardless of how clever our instruments become. The situation becomes even more interesting when expansion enters the picture. The universe is not static. It has been growing since its earliest moments, and this growth happens to the fabric of space itself. Galaxies are not flying through a fixed cosmic stage. The stage is stretching, carrying galaxies along with it like raisins embedded in expanding dough. The further apart two regions are, the faster they recede from each other due to this expansion. This is the relationship encoded in what cosmologists call Hubble's law, named after the astronomer who first measured the effect in the 1920s. When light travels through this expanding medium, something remarkable happens to it. The wavelengths get stretched along with the space they pass through. A photon emitted as visible light in a distant galaxy may arrive at our telescopes as infrared or radio waves, depending on how long it has been traveling and how much expansion occurred during the journey. This phenomenon, called cosmological redshift, is one of the primary tools astronomers use to measure distance and infer the history of the universe. The greater the redshift, the longer the light has been traveling, and the more space has stretched during that travel. But redshift also reveals something more subtle and important. It tells us that the journey of light is not simply a matter of crossing a static distance. It is a journey through a medium that is itself changing during the crossing. Imagine a marathon runner trying to reach a finish line while the track itself is constantly being extended. Even if the runner maintains a steady pace, the effective distance keeps growing. The runner may eventually arrive, but the time required is longer than a naive calculation would suggest, and the runner ends up much farther from the starting point than the original track length implied. Photons in our expanding universe behave in just this way. Light from a galaxy that was, say, 3 billion light-years away when it emitted the light we now receive has spent more than 3 billion years traveling toward us, because the space between us has been stretching during the entire trip. By the time the light arrives, That galaxy is much farther away than it was when the photons started their journey. This is why the observable universe extends to a present-day distance of roughly 46 billion light-years, even though the universe is only 13.8 billion years old. The light has had 13.8 billion years to travel, but the source regions have been carried away by expansion to much greater distances. There is a critical implication hiding in this geometry. If expansion is fast enough, light from sufficiently distant regions can never reach us, no matter how long we wait. Imagine the same marathon runner, but now the track is extending faster than the runner can move. The finish line recedes faster than the runner approaches it. The runner can run forever and never arrive. In the universe, this is not a hypothetical. It is the actual situation for regions beyond a certain distance. The space between us and those regions is expanding faster than light can cross it. Photons emitted from those regions are racing toward us, but the cosmic fabric is opening up faster than the light can close the gap. Those photons will never arrive. The information they carry is, for all practical and theoretical purposes, permanently inaccessible. This is not a violation of relativity, even though it might sound like one. Special relativity prohibits objects from moving through space faster than light. It does not prohibit space itself from expanding at any rate. The galaxies are not flying through space at superluminal speeds. They are essentially stationary in their local regions, while the space between them stretches without limit on what it can do. This distinction is subtle but crucial. It means the cosmic speed limit applies to motion within space, not to changes in the size of space itself. The consequences for observation are profound. There are regions of the universe whose light is currently traveling toward us and will eventually arrive. There are regions whose light has been traveling and has already arrived, which we see as distant galaxies in our telescopes. And there are regions whose light has been traveling toward us for billions of years but will never arrive because expansion is winning the race. These last regions exist within the actual universe but lie outside any possible observation. We can write equations describing them, but we cannot detect them. They are, in a real sense, beyond science. The cosmic microwave background, that ancient radiation released when the universe became transparent, provides the practical horizon of what we can directly observe. Before that radiation was emitted, the universe was filled with hot ionized plasma that absorbed and scattered photons too quickly for them to travel any meaningful distance. The microwave background is the wall behind which our telescopes cannot peer using ordinary light. We can use other signals, like neutrinos or gravitational waves, to probe slightly further back, but these too have limits. Eventually, every form of physical signal hits a barrier of either time, opacity, or expansion. There is always a final horizon beyond which no information can pass. What this means is that our observational reach is fundamentally bounded. We can refine our techniques. We can build larger telescopes, more sensitive detectors, more sophisticated analysis tools. We can extract incredible amounts of information from the photons that do reach us. But we cannot extend our perception beyond the limits imposed by the speed of light, combined with the expansion of space. There will always be more universe beyond what we can see. The question, then, is not whether there is something beyond our horizon. The question is, what that something is, how much of it there is, and whether we have any reasonable way to characterize it through indirect means. To begin answering that question, we need to look more carefully at the expansion itself, at the strange and accelerating way that space behaves over cosmic scales, and at the rules governing how reality stretches into regions we may never visit. Expansion is not a single phenomenon. It is a complex process that is unfolded across the entire history of the universe, taking different forms at different epochs, governed by changing balances among the forces that shape the cosmos. To understand what lies beyond our observable horizon, we need to understand how this expansion behaves, particularly in the most distant regions, because it is the expansion itself that hides those regions from view. In the simplest description, expansion means that the distance between any two sufficiently separated points in the universe increases over time. Two galaxies that are not gravitationally bound to each other will, on average, find themselves further apart as the eons pass. This expansion is uniform in a statistical sense. There is no preferred direction, no center, no edge from which everything is fleeing. Every observer in the universe sees distant galaxies receding in every direction, and every observer concludes that they are at the center of the expansion. This is not a paradox. It is a natural consequence of the geometry of an expanding space. There is no actual center because the expansion happens everywhere at once. The rate of expansion is described by a quantity called the Hubble parameter, which relates how fast a distant region is receding to how far away it is. The current value of this parameter, often called the Hubble constant, has been measured by multiple independent methods. It tells us that for every megaparsec of distance, which is about 3.26 million light-years, the universe is expanding at roughly 70 kilometers per second. So a galaxy 10 megaparsecs away is receding from us at 700 kilometers per second on average. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. The further out you go, the faster the recession, in direct proportion to the distance. This linear relationship has a critical breaking point. At a sufficient distance, the implied recession velocity exceeds the speed of light. This distance is called the Hubble radius, and it currently sits at approximately 14.5 billion light-years. Galaxies beyond that distance are receding from us faster than light can travel. They are not violating any physical law because they are not moving through space faster than light. The space between us and them is simply stretching faster than light can cross it. From our perspective, however, the effect is similar to motion. Their light cannot catch up to us if it has not already done so. Now, here is where the situation becomes particularly strange. We can still see many galaxies that are currently beyond the Hubble radius. This seems paradoxical at first glance. If those galaxies are receding faster than light, how can their light reach us? The answer lies in the history of expansion. The light from those distant galaxies was emitted long ago, when the universe was smaller and the expansion was behaving differently. At the time of emission, the gap between the source galaxy and our location was within the reach of light. Photons left the source, began crossing the intervening space, and slowly made progress despite the stretching. As the universe expanded, the rate at which space grew between distant points evolved, and for much of cosmic history, the photons were able to make headway. Now, those photons are arriving at our telescopes, even though the source galaxies have since drifted to positions beyond the Hubble radius. This is the curious geometry of an expanding cosmos. Light arriving today may have come from regions that are now unreachable by any new signal. The galaxies we observe in the most distant Hubble images are showing us what they looked like billions of years ago. Their present state, whatever it may be, is forever beyond our ability to learn. By the time any new light they emit could reach us, the expansion will have pushed them too far away, and the photons will fall short like sprinters in a track that grows faster than they can run. The expansion has not been uniform across cosmic history. Different epochs have seen different behaviors. In the very earliest moments after the beginning, expansion was driven by a process called inflation, which we will examine in greater detail later. Following that initial burst, the universe expanded more sedately, with the rate gradually slowing due to the gravitational attraction of all the matter and energy contained within it. For most of cosmic history, expansion was decelerating. The mutual gravitational pull of galaxies was working against the expansion, slowing it down, and many cosmologists in the early 20th century assumed this deceleration would eventually halt expansion entirely, possibly even reversing it into a contraction that would end in a fiery collapse. That picture changed dramatically in the late 1990s. Two independent research teams studying distant supernovae made a discovery that overturned established assumptions. By measuring the brightness and redshift of a particular class of stellar explosions, they were able to map the expansion rate of the universe at different times in its history. What they found was unexpected. The expansion was not slowing down, it was speeding up. Some unknown influence was pushing space apart faster and faster as time progressed. Whatever was causing this acceleration was given a placeholder name: dark energy. The label captures both its mysterious nature and the fact that it carries energy distributed throughout space, driving expansion against the inward pull of gravity. The discovery of dark energy transformed cosmology. It meant the universe is not coasting toward an eventual stop, nor heading toward a future collapse. It is speeding outward, with the rate of acceleration determined by the density of this dark energy and the structure of space itself. The exact nature of dark energy remains one of the most important open questions in physics. It might be a property of empty space, sometimes called the cosmological constant. It might be a dynamic field that changes with time. It might be evidence that our current theory of gravity is incomplete and needs to be modified at the largest scales. Several hypotheses compete, and ongoing observations are gradually constraining the options, though no decisive answer has emerged. Whatever dark energy is, its presence guarantees a particular fate for the cosmos. As long as it continues to behave as it currently does, expansion will accelerate indefinitely. Galaxies currently visible to us will, over time, recede beyond our future horizon and disappear from view. Each year, a small but measurable amount of the universe drifts past the point of no return. This process is slow on human timescales, but over billions of years it produces dramatic effects. Eventually, all galaxies outside our local group will recede beyond reach, leaving our region of the cosmos isolated in a vast darkness. Observers in the very distant future will look out at the sky and see only the merged remnants of our nearby galactic neighborhood, with no evidence of the broader universe at all. This future erasure of cosmic information has unsettling implications for cosmology itself. If the universe continues accelerating, future astronomers will be unable to discover the truth of cosmic expansion. They will see a small, isolated, gravitationally bound system surrounded by emptiness, with no redshift, no microwave background, no evidence of a larger cosmos. Without the data we currently have access to, they would have no reason to suspect that anything else ever existed. This means we live in a privileged epoch, scientifically speaking. We can see signs of the broader universe that future intelligences will never be able to detect. But what does this acceleration tell us about regions beyond our current horizon? It strongly suggests that those regions exist. The mathematics of cosmic expansion does not just apply to the part of the universe we can see. It applies wherever there is space, matter, and energy. There is no reason to expect that expansion suddenly stops at the edge of our observable bubble. The universe almost certainly continues with the same physical laws and the same expansion behavior, far beyond what our telescopes can reach. The exact extent of this continuation is unknown. Some estimates suggest the universe might be at least 250 times the diameter of the observable region. Others suggest it might be infinite. The data we currently have does not allow us to decide between these possibilities with certainty, but it does allow us to constrain them. There is another consequence worth noting. Because expansion is accelerating, the regions beyond our horizon are being carried away from us at an ever-increasing rate. Even if some of those regions are currently just barely beyond our reach, they are receding faster and faster. They are becoming more inaccessible, not less, with each passing eon. This means the cosmos beyond our horizon is not simply a place we cannot currently see. It is a place we will never see, and the gulf between us and it is growing wider with every passing moment. We are, in a sense, sealed within our local bubble of observation, watching the rest of reality drift forever out of reach. To better characterize this bubble, cosmologists have developed several precise definitions of the regions involved. The particle horizon, the event horizon, and the Hubble radius are three distinct concepts, each capturing a different aspect of how light and expansion interact. Understanding the distinctions among them is essential for anyone seeking to grasp what lies beyond what we can see. The relationships among these horizons reveal something important about the structure of space and the limits of cosmic knowledge, and they form the framework within which all further speculation about the universe beyond must be conducted. The Hubble volume is one of the most useful and frequently misunderstood concepts in modern cosmology. It refers to a specific region of space defined by a particular geometric condition. Within the Hubble volume, every point is close enough to us that the local rate of cosmic expansion has not yet carried it beyond the speed of light relative to our position. Outside the Hubble volume, the expansion of space exceeds the speed of light, and from our perspective, those regions are receding faster than any signal can travel between us. The radius of the Hubble volume is determined by dividing the speed of light by the Hubble constant. With current measurements, this works out to approximately 14.5 billion light years. So the Hubble volume is a sphere centered on our location with that radius. Every galaxy within this sphere is, at this moment, receding from us at less than light speed. Every galaxy beyond it is receding faster than light. This boundary is not the same as the edge of the observable universe. It is a different kind of horizon, defined by current expansion rather than by accumulated history. The distinction between the Hubble volume and the observable universe is one of the more subtle points in cosmology, and it confuses even experienced researchers from time to time. The observable universe, as we have seen, extends roughly 46 billion light-years in present-day distance because it includes everything from which light has had time to reach us, regardless of how fast those regions are currently receding. The Hubble volume, by contrast, includes only the regions whose current recession velocity is less than light speed. It is a smaller sphere nested inside the larger observable region, and it represents a sort of immediate dynamical neighborhood. The reason this distinction matters is that the Hubble volume defines the region where two-way communication is, in principle, still possible. Within this sphere, a signal sent from our location could, given enough time, reach a destination, and a signal sent from there could reach us. Beyond this sphere, expansion is currently outpacing the speed of light, which means signals sent now would never arrive at distant destinations. They would be carried backward in a relative sense, falling behind the expanding fabric of space. The Hubble volume thus defines a kind of present-day causal neighborhood. It is the realm in which the laws of physics permit mutual influence over indefinite time, subject to the future evolution of expansion. Even this concept comes with complications. Because expansion is accelerating, the Hubble volume itself is changing. The Hubble constant is not actually constant. It is a parameter that varies with cosmic time, and it has been decreasing for most of cosmic history. In the very early universe, the Hubble parameter was enormous, and the corresponding Hubble volume was tiny. As expansion proceeded and the universe became more diffuse, the Hubble parameter dropped and the Hubble volume grew. For a long time, this growth seemed straightforward. But with the discovery of dark energy and the realization that expansion is accelerating, the picture has become more nuanced. The Hubble parameter is now approaching a limiting value rather than continuing to decrease without bound. As a result, the Hubble volume is approaching a stable size, beyond which it will not significantly grow. This has profound implications for the long-term future of the universe. As expansion continues to accelerate, more and more of what we can currently observe will pass beyond the Hubble volume, and eventually beyond a related boundary called the cosmic event horizon. The event horizon is the surface beyond which no signal sent from our position now can ever reach. Anything currently inside the event horizon can still, in principle, receive a signal from us. Anything outside it cannot. The event horizon is currently at about 16 billion light-years in present-day distance, slightly larger than the Hubble radius, but much smaller than the observable universe. The event horizon will gradually contract in a real sense as expansion continues, isolating us further from regions that were once dynamically connected to ours. The interplay among the particle horizon, the Hubble volume, and the event horizon defines the structure of cosmic visibility. Each of these surfaces captures a different aspect of how time, space, and information interact. The particle horizon tells us how far we can see into the past. The Hubble volume tells us where current expansion exceeds light speed. The event horizon tells us how far our future signals can reach. Together, they describe the topology of cosmic communication, and they reveal that the universe is, in important ways, a network of disconnected regions, each of which can only ever exchange information with its own local neighborhood. To understand the practical meaning of this, consider a galaxy that is currently located 15 billion light-years away. This galaxy is inside our observable universe, because light from its past has had time to reach us. But it is outside the Hubble volume, because at 15 billion light-years, the local recession velocity exceeds the speed of light. We can see this galaxy, but only in its ancient form, as it existed when its light first began its journey toward us. The current state of that galaxy is hidden from us, because any signal it is emitting right now will never arrive. The galaxy has, in effect, two relationships with us, an observational one based on old light and a causal one that has been severed by expansion. We can study its past, but we cannot interact with its present. This duality applies to vast regions of the cosmos. Most of the galaxies we currently observe in deep-field images are in this strange state. Their light has reached us, but their causal connection to us is broken. We see them as cosmic fossils, frozen images of bygone eras, while their present circumstances unfold in regions we will never reach. The universe, in this sense, is a museum of light, displaying the deep past of regions whose current condition is permanently unknowable. There is something philosophically arresting about this. The information we have about the distant cosmos is fundamentally backward-looking. We are not exploring the universe as it is. We are exploring the universe as it was. Each photon arriving at our telescopes is a relic, a frozen sample of some past moment in some particular region. We assemble these samples into a coherent picture of cosmic history, but the picture is necessarily incomplete. The present state of most of the universe is unavailable to us, not just in practice, but in principle. The Hubble volume sets a limit on what we can causally interact with, and the event horizon sets a limit on what we can ever influence. Everything beyond these surfaces is, in different senses, isolated from us. Yet within this isolation, there are still rich relationships to study. The matter and energy inside our Hubble volume include billions of galaxies, vast clouds of gas, dark matter structures, and the lingering radiation from the early universe. We can probe the dynamics of these contents through gravitational interactions, electromagnetic emissions, and the cosmic microwave background. We can use the apparent positions and motions of distant objects to test theories of expansion. We can compare the structure of cosmic webs across different epochs to validate models of galaxy formation. The Hubble volume is not a small place. It is enormous on any meaningful scale, and the science of cosmology has used its contents to develop a remarkably detailed understanding of how the universe has evolved. But the question of what lies beyond remains. The Hubble volume is a boundary, not an end. The universe almost certainly continues past it with the same physical laws and the same general structure. The matter and energy that exist outside our Hubble volume are made of the same particles, governed by the same forces, organized into the same kinds of galaxies and stars that we see within our region, or at least, that is the standard assumption. Whether this assumption holds across truly vast distances is one of the deepest questions in cosmology, and it brings us to the issue of whether the universe is uniform on the largest scales. The cosmological principle, a foundational assumption of modern cosmology, states that on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same in every region, on average. Isotropic means it looks the same in every direction, on average. This principle is not arbitrary. It is supported by extensive observational evidence within our observable region. The cosmic microwave background, when measured across the entire sky, shows remarkable uniformity, with temperature variations of less than 1 part in 100,000. The distribution of galaxies, when averaged over large enough volumes, also appears statistically uniform. These observations suggest that, at least within our observable bubble, the universe is essentially the same everywhere. The question is whether this uniformity continues beyond what we can see. The standard assumption is that it does, that the cosmological principle holds across the entire universe, not just the portion we can observe. Under this assumption, The universe beyond our horizon contains galaxies, stars, planets, and possibly observers similar to those within our visible region. The total cosmos would be a vast extension of the local one, governed by the same rules and populated by the same kinds of structures. But this is an assumption, not a measured fact. We cannot test it directly. We can only check whether it is consistent with what we see and whether alternative hypotheses make different predictions that we could potentially distinguish. This brings us to the heart of the matter. What lies beyond the observable universe is a question that requires both observational data and theoretical reasoning to address. The data tell us about the contents of our region. The theory provides frameworks for extrapolating beyond it. The interplay of the two is how cosmology approaches questions that cannot be answered by direct observation alone. To make progress, we need to examine what the data actually say about the structure of space at the largest measurable scales and what those measurements imply about the regions that lie outside our visible horizon. The natural starting point for thinking about what exists beyond the observable horizon is to ask what kind of universe our local region is part of. If we can characterize the geometry, the contents, and the dynamics of the cosmos within our reach, we can begin to make reasoned extrapolations about what continues past the edge of our vision. This is not guesswork in the casual sense. It is a structured exercise in scientific inference, using observed data to constrain theoretical models, and then using those models to predict what should exist in regions we cannot directly observe. The most important measurement in this exercise is the geometry of space itself. Spaces can have different intrinsic shapes. A flat geometry, in which parallel lines remain parallel forever and the angles of a triangle sum to 180 degrees, is one possibility. A positively curved geometry, like the surface of a sphere, is another. In such a space, parallel lines eventually converge, and triangle angles sum to more than 180 degrees. A negatively curved geometry, sometimes likened to the surface of a saddle, is the third basic option. There, parallel lines diverge, and triangle angles sum to less than 180 degrees. The actual universe must have one of these geometries or some hybrid form, and the implications for the total size of the cosmos are substantial. A positively curved universe is necessarily finite in spatial extent, much like the surface of a sphere is finite, even though it has no edges. If you travel far enough in any direction in such a universe, you eventually return to where you started, having circumnavigated the cosmos itself. A flat or negatively curved universe, by contrast, is most naturally infinite in extent. There is no boundary, no edge, and no return to the starting point. You can keep traveling forever in any direction, encountering new regions of space without limit. The geometry, in other words, is closely tied to the total size of the universe. Measuring the curvature is one of the most direct ways of inferring how much cosmos exists beyond what we can see. The measurements have been carried out with increasing precision over the past few decades. The primary tool is the cosmic microwave background, which provides a kind of cosmic ruler. The microwave background contains tiny temperature fluctuations that correspond to physical structures of known size at the moment of emission. These structures, called acoustic peaks, were produced by sound waves traveling through the early universe before the radiation decoupled from matter. The physical size of these structures, called the sound horizon, can be calculated from basic physics. By comparing the calculated physical size to the apparent angular size we observe in the sky, we can determine how light has traveled across the universe to reach us, and therefore the geometry of space. The results have been consistent across multiple experiments. The Wilkinson Microwave Anisotropy Probe, the Planck satellite, and various ground-based observatories have all measured the curvature of space, and the answer is the same. Within measurement uncertainties, the universe appears to be flat. The deviation from perfect flatness, if any, is less than half of 1%. This is a remarkably precise result, and it has profound implications for the structure of the cosmos. If the universe is truly flat or very close to it, then the most natural interpretation is that it is infinite in spatial extent. An infinite universe means there is no edge, no boundary, no finite total size. The space we can observe is a small bubble within an unbounded continuation of similar space. Galaxies, stars, planets, and possibly observers exist in regions far beyond our horizon, in numbers that have no upper limit. Under this interpretation, the universe we see is not a special case, but a typical sample of an unbounded reality. However, flatness does not strictly require infinity. It is also possible to have a flat but finite universe through certain topological configurations. Imagine the surface of a torus, which is geometrically flat in a meaningful sense, but finite in extent. A universe with such a topology would be flat in local measurements, but would wrap around on itself at large scales, much like a video game world where flying off one edge returns you on the opposite side. Cosmologists have searched for evidence of such topology by looking for matching patterns in the cosmic microwave background. If the universe wraps around on a scale smaller than our observable horizon, we should see repeated features in the microwave sky, like multiple images of the same region. No such matching patterns have been found at any scale that fits within the observable universe, which suggests that if the universe is finite, it is at least many times larger than what we can see. The most popular interpretation, given all available data, is that the universe is flat and very large, possibly infinite. Even under the most conservative estimates that allow for some curvature within the measurement uncertainty, the total size of the universe is enormous compared to the observable region. The lower bound on the size of the cosmos, based on combined data from microwave background measurements and other cosmological observations, suggests that the universe is at least 250 times the diameter of the observable bubble. That means the actual universe is at least roughly 23,000 billion light-years across, and possibly much larger. Some estimates push this lower bound even higher, to thousands or millions of times the observable diameter, depending on the specific theoretical models considered. These numbers are staggering, but they are conservative. They represent only the minimum sizes consistent with current data. The actual size could be vastly larger. If the universe is truly infinite, then by definition there is no upper bound on its extent. In an infinite cosmos, anything that can happen with non-zero probability happens an infinite number of times. The implications of this are profound and somewhat dizzying, and we will return to them later. For now, the key point is that the data we have are consistent with a universe that extends far beyond our observable bubble, possibly without limit. The flatness of the universe is itself a curious feature that demands explanation. If you tried to construct a randomly initialized universe with arbitrary geometry, the chances of getting one that is precisely flat would be essentially zero. The fact that our universe appears flat to such high precision suggests that some physical process tuned the geometry during the early stages of cosmic evolution. This is one of the strongest pieces of evidence for the theory of inflation, which we will examine in detail shortly. Inflation predicts that any initial curvature would be smoothed out by the rapid expansion of the early universe, leaving the cosmos essentially flat, regardless of how it started. The observation of flatness is thus not just a measurement, but a confirmation of a specific theoretical scenario, one with profound implications for the size and structure of the universe. Another important measurement concerns the contents of the universe. We have evidence that the cosmos contains ordinary matter, like the atoms that make up stars and planets, dark matter, which is some kind of invisible substance that interacts gravitationally but not electromagnetically, and dark energy, which is the mysterious component driving accelerating expansion. The relative proportions of these components have been measured with considerable precision. Ordinary matter makes up about 5% of the total energy content of the universe. Dark matter makes up about 27%. Dark energy accounts for the remaining 68%. These numbers are consistent across multiple independent observations, and they form the basis of what cosmologists call the Standard Model of Cosmology, sometimes referred to as the Lambda CDM model. If we assume that the universe beyond our horizon has the same composition, then the regions outside our observable bubble contain the same kinds of matter and energy in the same proportions. They contain galaxies, stars, planets, and possibly life, in numbers far exceeding what we can see. The total amount of matter in the cosmos, under this assumption, vastly exceeds the amount within our observable region. If the universe is infinite, then the total amount of matter is also infinite. The cosmological principle, which states that the universe is homogeneous and isotropic on large scales, is the foundation of these extrapolations. Without it, we would have no way of inferring what lies beyond our horizon. The principle is supported by the uniformity of the cosmic microwave background and by the statistical similarity of galaxy distributions in different directions, but it is fundamentally an assumption. There is no way to verify it for regions we cannot observe. The assumption could be wrong. The universe might be inhomogeneous on scales larger than our observable region. There might be vast deserts where matter is absent, or dense concentrations beyond anything we have seen. The standard cosmological model assumes uniformity because it fits the data we have, not because we have direct evidence of uniformity at the largest scales. There are some hints, however, that the universe might not be perfectly uniform. Certain anomalies in the cosmic microwave background have puzzled cosmologists for years. A region known as the cold spot, which is colder than expected, and various asymmetries in the temperature pattern across the sky raise the possibility that something unusual exists either within or beyond our observable region. Most cosmologists consider these anomalies to be statistical fluctuations that fall within the expected range of randomness, but some researchers have proposed that they might be signatures of structure on scales larger than the observable universe, possibly even traces of interactions with regions beyond our horizon. Whatever the truth turns out to be, the measurements we have made tell us several important things. The universe is flat, or very nearly so. It is dominated by dark energy that is driving accelerating expansion. It contains ordinary matter and dark matter in well-defined proportions. It extends far beyond our observable horizon, with conservative estimates placing the total size at hundreds of times the diameter of what we can see, and many estimates suggesting it is infinite. The unseen cosmos is not a small annex attached to our visible region. It is, by any reasonable measure, the overwhelming majority of reality. This raises a natural question. If the universe is so vast and possibly infinite, what mechanism produced it? How does an entire cosmos come into being on such a scale? The answer, according to the most successful theoretical framework currently available, lies in the very first moments of cosmic history, in an event so brief and so explosive that it shaped everything that followed. To understand the structure and extent of the universe, we need to examine what happened during the first tiny fraction of a second after the beginning, when a process called inflation set the stage for everything we now see. Inflation is one of the most consequential ideas in modern cosmology. It proposes that the very early universe underwent a brief but extraordinary period of exponential expansion, during which the fabric of space stretched by an enormous factor in an almost vanishingly small interval of time. The theory was first developed in the late 1970s and early 1980s, primarily by the physicist Alan Guth, with significant contributions from Andrei Linde, Alexei Starobinsky, Paul Steinhardt, and others. It emerged as a solution to several long-standing puzzles in cosmology, and although it remains technically a theoretical framework rather than a directly observed phenomenon, it has accumulated remarkable observational support and has become the cornerstone of the standard cosmological model. To understand why inflation was proposed, we need to consider the puzzles it was designed to solve. The first is the horizon problem. When cosmologists examined the cosmic microwave background, they found that the radiation was almost uniform across the entire sky, with temperature variations of less than 1 part in 100,000. This uniformity is striking because, according to the standard expansion history without inflation, regions on opposite sides of the sky should never have been in causal contact. Light from one region would not have had enough time to reach the other since the beginning of the universe. Without any mechanism to share information, those regions should have evolved independently and ended up at different temperatures. Yet, they are essentially identical. How did distant regions of the universe achieve such precise thermal equilibrium without being able to interact? The second puzzle is the flatness problem. As we've already discussed, the universe appears to be geometrically flat to remarkable precision. But the equations governing cosmic evolution show that flatness is unstable. Any small initial deviation from perfect flatness should have grown enormously over cosmic time. For the universe to be as flat as we observe it today, it must have been even flatter in the past by an extraordinarily fine margin. The flatness problem asks why the universe was tuned with such precision at the beginning. The third puzzle is the absence of certain exotic relics that should have been produced during the high-energy phases of the early universe. Various theoretical considerations suggest that the very early cosmos should have produced large numbers of magnetic monopoles and other unusual particles. These should still be detectable today, yet none have been found. Where did they go? Inflation solves all three of these problems with a single mechanism. The idea is that during the first tiny fraction of a second after the beginning, the universe underwent a phase of rapid exponential expansion driven by a peculiar form of energy associated with a hypothetical field called the inflaton. This field had the property that its energy density remained essentially constant as space expanded, which is the condition needed to produce exponential growth. During this inflationary epoch, the universe is thought to have expanded by a factor of at least 10 to the 26th power, possibly far more, in an interval of perhaps 10 to the negative 32nd seconds. The numbers are staggering, but they emerge naturally from the equations of general relativity, combined with the assumed properties of the inflaton field. The consequences of this rapid expansion are profound. The horizon problem is solved because, before inflation, the regions that would later become opposite sides of the observable universe were close enough to be in thermal contact. They equilibrated to the same temperature, and then inflation stretched them apart to enormous separations while preserving that uniformity. The flatness problem is solved because exponential expansion drives any initial curvature towards zero. Whatever the initial geometry of the pre-inflationary universe, the stretching of space during inflation flattens it out to extreme precision, leaving the post-inflationary universe essentially flat regardless of the starting conditions. The monopole problem is solved because exotic particles produced before inflation are diluted to vanishing density by the enormous expansion, leaving the post-inflationary universe essentially empty of such relics. Inflation also makes a specific and testable prediction about the structure of the cosmos. Quantum fluctuations in the inflaton field, present during the inflationary epoch, would have been stretched by the rapid expansion to macroscopic scales. These stretched fluctuations would imprint themselves as tiny density variations across the post-inflationary universe. Over billions of years, these density variations would grow under gravity, eventually forming the galaxies, clusters, and large-scale structures we observe today. The cosmic microwave background, viewed at high resolution, shows precisely the kind of fluctuations that inflation predicts. The angular spectrum of these fluctuations matches inflationary models with remarkable accuracy, providing strong observational support for the theory. But the implications of inflation go far beyond solving the original puzzles. The theory has profound consequences for the size and structure of the universe. During inflation, the cosmos expanded by such an enormous factor that any region that was initially within causal contact was stretched to scales far larger than what we can currently observe. The observable universe, in this picture, is just a small patch of a much larger region that all came from the same initial pre-inflationary domain. The actual universe, in the inflationary picture, is vastly larger than what we can see. The question is, how much larger? Different versions of inflation give different answers. The simplest models, with the minimum amount of inflation needed to solve the original puzzles, suggest that the universe is at least a few hundred times the diameter of the observable region. But there is no upper limit imposed by the basic theory. Many models allow for or even require far more inflation than the minimum, producing a universe many orders of magnitude larger than the observable bubble. Some models suggest the universe is so vast that the observable region represents an essentially infinitesimal fraction of the whole. The size implications become even more dramatic when we consider what happens to quantum fluctuations during inflation. The very same fluctuations that produce the density variations responsible for galaxy formation also produce variations in the inflating field itself. In some regions, the inflating field has a value that ends inflation slightly earlier than average. In other regions, it has a value that prolongs inflation. The regions where inflation lasts longer end up much larger than the regions where it ends sooner, because exponential expansion magnifies any difference enormously. This means that the universe is not uniform on the largest scales. Different regions experience different amounts of inflation, producing different local conditions. The consequence is that the universe contains an enormous variety of regions, all stretched out from a single pre-inflationary domain. Most of these regions are far beyond our observable horizon. We can never directly observe them. But the theory of inflation, combined with the observed properties of our local region, allows us to infer their existence and characterize their general properties. This leads to one of the more startling extensions of inflationary theory. If inflation can happen once, can it happen again? Can it happen in multiple places at once? Can it produce a never-ending cascade of inflating regions, each producing its own universe? The answer, according to many cosmologists, is yes. This is the idea of eternal inflation, and it is one of the most provocative concepts in modern cosmology. We will examine it in detail in the next section. But before moving on, it is worth pausing to appreciate what inflation tells us about the universe beyond our horizon. The theory predicts that the cosmos is far larger than what we can see, with regions that were stretched apart by the rapid expansion of the early universe to distances we will never reach. These regions contain matter and energy, governed by the same physical laws as our local region, organized into galaxies and stars and possibly observers. They are part of the same continuous universe as us, but they are causally disconnected by the gulf of space that inflation produced. We share a common origin with them, but we will never make contact. There is something deeply unsettling about this conclusion, and also something deeply liberating. The universe is far grander than our observations alone could suggest. The cosmos extends in directions we cannot trace, populated by structures we cannot photograph, governed by laws that should be the same as our own but might, in some scenarios, differ in ways we cannot predict. We are not at the center of anything special. We are observers in a small region of an unimaginably vast reality, peering out at a thin shell of light that represents only the most accessible fraction of what exists. The evidence for inflation is strong but not conclusive. The cosmic microwave background shows patterns consistent with inflationary predictions. The large-scale distribution of galaxies fits inflationary models. The geometry of space is flat, as inflation predicts. But there are alternative theories that can produce similar predictions, and the specific mechanism of inflation remains poorly understood. The inflating field has not been directly detected. Its properties are inferred from the observed consequences rather than from any direct experimental probe. Different versions of inflation make slightly different predictions, and observational efforts are ongoing to distinguish among them. One important observational signature would be the detection of primordial gravitational waves. Inflation predicts that the rapid expansion of the early universe would have produced ripples in spacetime that should still be detectable today, imprinted as a specific polarization pattern in the cosmic microwave background. Several experiments are currently working to detect this signal, including ground-based telescopes at the South Pole and future satellite missions. A definitive detection would provide direct evidence of inflation and would help discriminate among different inflationary models. A non-detection, on the other hand, would constrain the parameter space of possible inflationary scenarios. So far, the gravitational wave signal has not been definitively detected, but the limits placed on it are continuously improving. Whatever the specific details of inflation turn out to be, the general framework has reshaped our understanding of the cosmos. The universe is far larger than what we can directly observe, and the mechanism that produced this vast extent operated in the first tiny fraction of a second after the beginning. The observable region is just a small sample of a much larger cosmos, and the boundaries of our vision are not the boundaries of reality. To understand what lies beyond, we need to follow the inflationary logic further into territory where the implications become even more remarkable. We need to examine the possibility that inflation never truly ended, that it continues somewhere even now, producing new universes in an endless cascade that stretches the very concept of cosmos to its limits. Eternal inflation is one of those ideas that begins as a technical observation and ends up reshaping how we think about the nature of reality. The concept arose when cosmologists pushed the equations of inflation a little further than the original theorists had intended, looking carefully at what happens in regions where the inflating field, the hypothetical entity driving inflation, behaves slightly differently from the average. The results were unexpected and, to many researchers, profound. The basic idea is straightforward. During the inflationary epoch, the inflating field has a particular value that determines the rate of expansion. Over time, the field slowly evolves toward a state where inflation ends, releasing its energy into ordinary matter and radiation in a process called reheating. This is what happened in our region of the universe, leading to the hot, dense state that we identify with the Big Bang and to the subsequent evolution of stars and galaxies. The standard picture is that inflation ended everywhere at roughly the same time, producing a uniform post-inflationary cosmos. But this picture is too simple. The inflating field is subject to quantum fluctuations, just like every other field in physics. These fluctuations are small on the scale of any given moment, but they have important cumulative effects. In some regions, the random quantum jitter pushes the field slightly toward the value where inflation ends, accelerating the transition to ordinary expansion. In other regions, the jitter pushes the field in the opposite direction, prolonging inflation. The regions where inflation continues are stretched even more by the ongoing exponential expansion, growing to much larger sizes than the regions where it has ended. The consequence is striking. Even when most of the inflating field has evolved to the point where inflation should end, there are always some regions where quantum fluctuations have kept the field in the inflating state. These regions continue to expand exponentially while the surrounding regions exit inflation. And because exponential expansion makes the inflating regions grow extraordinarily quickly, they end up dominating the total volume of space. The inflationary process, once started, may never fully end. There may always be some regions where it continues, producing new space at a staggering rate, while other regions exit inflation and become ordinary universes like ours. This is the essence of eternal inflation. It is not a separate theory from standard inflation. It is a natural consequence of standard inflation when the role of quantum fluctuations is fully accounted for. Many cosmologists, including André Lande, Alexander Vilenkin, and others, have argued that eternal inflation is generic, meaning it happens in almost any version of inflation that fits the observations of our local region. The conclusion is that inflation, once it begins, is essentially self-perpetuating, generating an endless succession of inflating and non-inflating regions throughout an eternally growing cosmos. The implications of this are remarkable. If eternal inflation is correct, the universe we observe is just one of an unimaginable number of pocket universes that have formed within a much larger inflating background. Our pocket universe formed when our local region of the inflating field happened to evolve to the value that ends inflation. The energy released during that transition produced the hot, dense state of our early cosmos, and subsequent expansion produced the observable universe we now inhabit. But while this was happening in our region, other regions continued to inflate, and still others underwent their own transitions to ordinary expansion, producing their own pocket universes. The process goes on indefinitely, creating new universes at a rate that vastly exceeds the rate at which any single universe ages and dies. The structure of this larger reality is sometimes called the multiverse, although the term is used in several different senses across different theories. In the context of eternal inflation, the multiverse refers specifically to the collection of pocket universes generated by the eternally inflating background. Each pocket universe is internally consistent with its own history, its own stars and galaxies, and its own physical processes. From the inside of any particular pocket universe, an observer would see a hot, dense state at some past moment, followed by expansion and cooling, leading to the formation of structures and eventually to whatever conditions allow for observation. The fact that the pocket universe is embedded in a larger, eternally inflating background would not be directly visible to the observer, because the surrounding inflating regions would be receding so fast that no signal could reach them. This means that if eternal inflation is correct, our observable universe is not just a small patch of a slightly larger cosmos. It is a tiny island within an unbounded sea of inflating space, separated by enormous gulfs from countless other islands, each containing its own universe. The total volume of this multiverse, if eternal inflation has been going on for any significant length of time, is essentially infinite. New pocket universes are constantly being produced. Old ones are evolving through their own cosmic histories. The whole structure is a vast hierarchy of universes within universes, with no overall beginning and no overall end. There is an even more provocative aspect to this picture. In many models of inflation, the inflatant field does not have a single fixed value where inflation ends. Instead, it has a complicated landscape of possible final states, each corresponding to slightly different post-inflationary physics. Different pocket universes may end up with different values for fundamental constants. The strength of gravity might be different in one pocket universe than in another. The masses of elementary particles might differ. The cosmological constant, which determines the rate of accelerating expansion, might take on a range of values. Even the number of spatial dimensions might vary from one region to another, depending on the specifics of the underlying physical theory. This idea connects to a much broader concept that has emerged from string theory and related frameworks. String theory, which is one of the leading candidates for a unified theory of physics, suggests that the laws of nature we observe are not absolute, but are instead determined by the specific configuration of higher dimensional structures called branes and the fields that exist on them. There are an enormous number of possible configurations, sometimes estimated to be at least 10 to the 500th power, each producing different effective physics. If eternal inflation populates pocket universes with all these different configurations, then the multiverse contains an extraordinary variety of physical environments, most of which would be completely inhospitable to anything resembling life as we know it. In this picture, the universe we observe is not a typical sample of all possible universes. It is one of the relatively rare pocket universes whose physical constants happen to allow for the formation of stable atoms, complex chemistry, and eventually life. Most pocket universes would have constants tuned in ways that prevent any interesting structure from forming. Without the right balance of forces, there would be no stars, no galaxies, no chemistry. Most universes would be sterile cosmic deserts. The fact that we find ourselves in a universe with the right conditions for life is, in this view, not a coincidence but a selection effect. Observers can only exist in universes where observers can exist. This is sometimes called the anthropic principle, and it has been used to explain some otherwise puzzling features of our cosmos, including the surprisingly small but non-zero value of the cosmological constant. The combination of eternal inflation and the string theory landscape produces what is sometimes called the multiverse picture. It is a remarkable extension of standard physics, transforming the question of what lies beyond our observable horizon from a simple matter of more of the same into a vastly more complex scenario involving multiple universes with potentially different physical laws. The actual cosmos, in this view, is not just larger than what we can see. It is fundamentally more diverse, containing regions where the very rules of physics differ from those in our local domain. It is important to note that this is all theoretical. Eternal inflation has not been directly observed, and the existence of pocket universes with different physical constants is by definition beyond direct verification. The theory is built on extrapolations from observed phenomena, supported by mathematical consistency and by its ability to explain certain features of our cosmos. But it is not a theory we can test in the same way we can test predictions about the cosmic microwave background or the distribution of galaxies. Some cosmologists embrace the multiverse picture enthusiastically. Others remain skeptical, arguing that without direct evidence, the multiverse is not really a scientific concept, but rather a kind of philosophical or metaphysical speculation. The skepticism is not unreasonable. A scientific theory typically gains acceptance through its ability to make testable predictions and to be either confirmed or refuted by observation. The multiverse, by virtue of being mostly beyond observation, is difficult to test directly. We can only test it indirectly by examining whether its predictions about the local universe match what we see. To some extent, those predictions do match. The flatness, uniformity, and overall structure of our cosmos are consistent with the inflationary picture. But these features can also be produced by simpler theories that do not require the full multiverse framework. The decision to accept or reject the multiverse depends to a considerable extent on theoretical considerations that go beyond what current observations can decide. There is, however, one tantalizing possibility for indirect evidence. If different pocket universes can collide, the collisions might leave detectable signatures in the cosmic microwave background. Such a collision would produce a specific kind of pattern, perhaps a circular feature, or a temperature variation with particular characteristics that could in principle be identified in high-resolution maps of the microwave sky. Several researchers have searched for such features, and a few candidate signals have been proposed, although none has been definitively confirmed. The hunt continues, and future microwave background experiments may shed more light on this question. Even without direct evidence, the idea of eternal inflation has profound implications for how we think about the universe beyond our horizon. If the theory is correct, the cosmos is far larger and far more varied than our local observations can suggest. The universe is not a single thing, but a hierarchy of regions, with our observable bubble being just a tiny portion of one pocket universe within an unbounded multiverse. The physical laws we have discovered may not apply universally. They may be local features of our particular pocket, determined by the specifics of how inflation ended in our region. The actual rules governing the larger reality may be considerably more complex, encompassing a wider range of possible physical environments than anything our local cosmos contains. This is a heady conclusion, and it leads naturally into a deeper exploration of the multiverse concept. The eternal inflation picture is just one version of the multiverse idea. There are several others, drawn from different theoretical frameworks, each proposing a different way in which our universe might be part of a larger reality. Some of these alternatives are closely related to eternal inflation. Others arise from entirely different considerations, like quantum mechanics or higher dimensional physics. Each offers a different perspective on what lies beyond our observable horizon, and each has its own observational consequences and theoretical motivations. To explore the full range of possibilities, we need to step back from inflation specifically and examine the broader landscape of multiverse theories that have been proposed in recent decades. The many worlds interpretation of quantum mechanics offers a radically different route to the multiverse idea, one that does not begin with cosmic inflation or the expansion of space, but with the behavior of matter and probability at the smallest measurable scales. Unlike eternal inflation, which proposes separate regions of space-time isolated by vast distances and accelerating expansion, the quantum multiverse emerges from the mathematics governing wave functions, measurement, and the strange persistence of quantum uncertainty. In classical physics, the universe behaves predictably. A planet follows a trajectory. A stone falls in a calculable arc. If the initial conditions are known precisely enough, the future can, in principle, be determined. Quantum mechanics disrupted this picture completely. At microscopic scales, particles do not possess single definite states prior to observation. Instead, they are described by wave functions, mathematical objects encoding multiple possible outcomes simultaneously. An electron passing through an apparatus may exist in overlapping states associated with different positions, energies, or directions of motion. The equations do not select one possibility over another. They evolve all possibilities together. The difficulty emerges when a measurement occurs. In the traditional Copenhagen interpretation of quantum mechanics, the act of observation causes the wave function to collapse into a single outcome. Before measurement, multiple possibilities coexist mathematically. After measurement, only one remains physically real. But this raises an uncomfortable question. What precisely counts as a measurement? At what moment does possibility become reality? The equations themselves do not specify a mechanism for collapse. The collapse is inserted as an additional rule, separate from the ordinary evolution of the wave function. In the 1950s, the physicist Hugh Everett proposed a startling alternative. Suppose the wave function never collapses at all. Suppose every possible outcome described by quantum mechanics actually occurs, but in different branches of reality. Under this interpretation, measurement does not reduce possibilities into a single world. It separates the observer into multiple versions, each experiencing one outcome among many. The universe continuously branches into parallel histories, all equally real, all evolving independently after the split. The implications are difficult to visualize because human intuition evolved in a classical environment where only one outcome appears to occur. Yet the mathematics of quantum mechanics works perfectly well without collapse. In Everett's framework, reality becomes a constantly branching structure of parallel universes generated by ordinary quantum interactions. Every microscopic event with multiple possible outcomes produces further branching. A radioactive atom decays in one branch and remains stable in another. A photon reflects here and passes through there. Over time, these tiny divergences accumulate into vastly different macroscopic histories. A single quantum event, insignificant on its own, can eventually alter the development of entire civilizations. Tiny molecular differences can influence neural activity, which can influence human decisions, which can alter history itself. In one branch, a scientist makes a discovery slightly earlier. In another, a spacecraft mission fails. In another, a species never evolves at all. The many worlds interpretation implies that all physically possible histories consistent with quantum mechanics exist simultaneously within an unimaginably vast branching structure. What makes this especially relevant to the question of what lies beyond the observable universe is that these branches are not separated by ordinary distance. They occupy the same underlying quantum reality but evolve independently because of a process called decoherence. Decoherence occurs when quantum systems interact with their environments, causing different branches of the wave function to lose the ability to interfere with one another. Once decoherence has occurred, the branches become effectively isolated. Observers within one branch cannot communicate with or detect the others, even though all continue to exist within the larger mathematical structure. This produces a strange parallel with the cosmological horizon. In eternal inflation, other universes are separated from us by expanding spacetime that no signal can cross. In the quantum multiverse, other branches are separated not by space, but by decoherence, a kind of informational isolation built into the structure of quantum interactions themselves. In both cases, reality contains inaccessible domains that remain forever beyond direct observation. The many worlds interpretation remains controversial, though less so than it once was. Some physicists regard it as the simplest interpretation because it removes the arbitrary concept of wave function collapse and allows the equations of quantum mechanics to operate universally without exception. Others object that it multiplies realities extravagantly, generating an infinite proliferation of unseen worlds without observational necessity. Yet, despite the philosophical debate, the interpretation is fully compatible with all known experimental results. No observation has ever disproven it. One of the more unsettling consequences of the many worlds picture is that it removes any uniquely privileged history. The reality experienced by any observer becomes just one thread within an enormous branching network of alternatives. Every decision, every interaction, every quantum fluctuation contributes to further branching. There is no single cosmic storyline, only a constantly diversifying structure of parallel histories unfolding simultaneously. This idea begins to blur the distinction between cosmology and information theory. The universe is no longer merely a collection of objects moving through space. It becomes a structure of evolving informational states, with branching realities emerging from the probabilistic framework of quantum mechanics itself. And once reality is viewed in informational terms, another possibility emerges, one that shifts the discussion away from inflation and quantum branching entirely and towards something even stranger. The idea that space-time itself may not be fundamental at all, but instead may emerge from deeper structures hidden beneath the fabric of the observable universe. For most of human history, space and time were treated as the unquestioned stage on which reality unfolds. Matter moves through space, events occur through time. Even Einstein's theory of relativity, despite radically changing how space and time behave, still treated space-time as a real geometric structure underlying the universe. But over the last several decades, a growing number of physicists have begun to suspect that space-time may not be fundamental at all. It may be an emergent phenomenon, something that arises from deeper microscopic processes, the same way temperature emerges from the motion of atoms or fluid behavior emerges from molecular interactions. This possibility changes the question of what lies beyond the observable universe in a profound way. If space-time itself is emergent, then asking what exists beyond the observable horizon may be incomplete. The deeper question becomes what exists beneath space-time, what underlying structure gives rise to the geometry we experience as reality, and whether the observable universe is only a local feature embedded within something much larger and more abstract. One of the first clues pointing in this direction came from black hole physics. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered something deeply unexpected. Black holes are not completely black. Quantum effects near the event horizon allow them to emit radiation very slowly, causing them to lose energy and eventually evaporate over immense spans of time. More importantly, black holes possess entropy, a quantity associated with information and microscopic complexity. But the entropy of a black hole does not scale with its volume. It scales with the area of its event horizon. This was profoundly strange. In ordinary systems, entropy is proportional to volume because the number of microscopic configurations depends on how much space the system occupies. A gas filling a container has entropy determined by the number of ways its molecules can be arranged throughout the volume. But black holes behave differently. Their entropy depends only on surface area, suggesting that the information describing the contents of a region might somehow be encoded on its boundary. From this observation emerged one of the most important theoretical ideas in modern physics, the holographic principle. Proposed most prominently by Gerard T. Hooft and Leonard Susskind, the principle suggests that the entire informational content of a region of space can be represented on a lower dimensional boundary surrounding it. In a certain sense, the three-dimensional reality we experience may be analogous to a projection generated from information encoded on a distant surface. The idea sounds abstract, but it gained powerful support through developments in string theory. In the late 1990s, the physicist Juan Maldacena discovered a remarkable mathematical relationship known as the ADS-CFT correspondence. The relationship showed that a gravitational universe existing in a higher dimensional spacetime could be mathematically equivalent to a quantum theory without gravity defined on its lower dimensional boundary. Two entirely different descriptions of reality turned out to encode the same physics. This duality suggested something extraordinary. Gravity and spacetime themselves might emerge from more fundamental quantum interactions occurring in lower dimensional systems. The geometry of space could arise from patterns of entanglement and information rather than existing as a basic ingredient of nature. In this view, spacetime resembles a large-scale collective phenomenon, much like waves emerging from the coordinated motion of water molecules. If this is correct, then the observable universe may not be a self-contained structure at all. The galaxies, stars, and cosmic expansion we observe could emerge from deeper informational processes inaccessible to ordinary observation. The cosmological horizon would no longer represent merely the limit of visible space. It would represent the limit of a particular emergent description, beyond which the deeper structure generating spacetime might behave in ways fundamentally unlike the geometry we are familiar with. Some theoretical physicists have explored whether spacetime itself is built from networks of quantum entanglement. Entanglement is one of the strangest features of quantum mechanics. When particles become entangled, their properties remain correlated even across enormous distances. Measuring one instantly constrains the possible outcomes for the other, regardless of separation. Einstein famously disliked this implication, referring to it as spooky action at a distance, though later experiments confirmed that entanglement is a genuine property of nature. More recent theoretical work suggests entanglement may do more than correlate distant particles. It may actually generate the connectivity of spacetime itself. According to this perspective, regions of space remain geometrically connected because their underlying quantum states are entangled. Reduce the entanglement sufficiently, and the spacetime connection weakens or disappears. Space itself may emerge from patterns of informational relationships. This idea has led some researchers to propose that geometry is secondary, not primary. Distance may not be fundamental. Instead, what we perceive as spatial separation could emerge from the structure of deeper quantum relationships. If so, asking what exists beyond the observable universe becomes much more complicated, because the larger reality may not even obey ordinary spatial concepts. The underlying structure generating our universe may not possess directions, distances, or locations in the way human intuition expects. There are additional hints pointing toward this possibility. Quantum gravity, the long-sought attempt to unify general relativity with quantum mechanics, consistently encounters difficulties when spacetime is treated as continuous down to arbitrarily small scales. At extremely tiny distances, roughly the Planck scale, the smooth geometry described by relativity appears to break down. Quantum fluctuations become so violent that spacetime itself may lose definite structure. Some theories describe this regime as a kind of quantum foam, where geometry fluctuates constantly and conventional notions of position and duration cease to have stable meaning. Loop quantum gravity, one candidate theory of quantum gravity, proposes that space is not continuous at all, but composed of discrete units woven together in network-like structures called spin networks. According to this framework, spacetime resembles a fabric built from finite informational elements rather than an infinitely divisible continuum. The smooth space we experience would emerge only at larger scales, much like a digital image appears continuous from a distance despite being composed of individual pixels. String theory approaches the problem differently. Instead of treating particles as point-like objects, it models them as tiny vibrating strings existing within higher dimensional spaces. Different vibration modes correspond to different particles and forces. The mathematics of the theory requires additional spatial dimensions beyond the familiar three, dimensions that may be compactified or hidden at scales too small to observe directly. In some versions of the theory, our entire observable universe exists on a three-dimensional membrane, or brane, embedded within a higher dimensional structure called the bulk. If this picture is correct, then the observable universe is only a localized region within a much larger multidimensional reality. Gravity may leak into extra dimensions, while electromagnetic and nuclear forces remain confined to our brane. Other branes may exist nearby in higher dimensional space, containing entirely separate universes inaccessible to ordinary observation. Under certain conditions, collisions between branes could even trigger events resembling Big Bangs, potentially offering an alternative explanation for the origin of our universe. These ideas remain speculative, but they arise naturally from attempts to reconcile the deepest theories in physics. The more closely scientists examine the foundations of reality, the more space-time begins to resemble an emergent approximation rather than an ultimate framework. The observable universe, once imagined as the totality of existence, increasingly appears to be one layer of description embedded within deeper and possibly far stranger structures. There is a recurring pattern here. Every time science pushes against a perceived boundary, the boundary dissolves into something larger. Earth was once believed to be the center of creation until astronomy revealed a solar system. The solar system became one small region within a galaxy. The galaxy became one among trillions within the observable universe. Then, the observable universe itself became a local bubble within a much larger cosmic structure. Now, even space-time may not be fundamental. Reality continues receding beyond each conceptual horizon we establish. This progression raises an uncomfortable possibility. Human intuition may simply be poorly adapted for understanding the largest and deepest layers of reality. Our brains evolved to navigate survival problems within a narrow range of scales and speeds. The concepts of space, time, locality, and causality that feel natural to us may be approximations useful only within ordinary environments. At cosmic or quantum extremes, those intuitions begin to fail. Yet despite these limitations, mathematics continues to extend our reach. Equations allow physicists to model realities that cannot be directly visualized. Entire frameworks describing higher dimensions, quantum geometries, and emergent spacetime can be manipulated consistently, even when they resist intuitive understanding. This is one of the defining features of modern physics. The universe is not obligated to conform to human expectation. It only needs to obey the mathematical structures governing its behavior. But mathematics alone does not guarantee physical truth. Many elegant theories exist that may never describe reality. The challenge is determining which abstractions correspond to the actual universe and which are merely artifacts of human reasoning. Observational evidence remains the ultimate test, and this creates a severe problem for theories involving regions beyond the observable universe or structures beneath spacetime itself. How can science investigate domains that may be permanently inaccessible? One strategy involves searching for indirect signatures. If higher dimensions exist, they might subtly alter the behavior of gravity at small scales or high energies. If our universe collided with another brane in the distant past, traces of that event might remain imprinted in the cosmic microwave background. If spacetime emerges from quantum entanglement, measurable relationships between gravity and information might eventually reveal themselves in black hole physics or quantum computing experiments. Physicists are searching for such signatures constantly, trying to connect speculative frameworks to observable consequences. Another strategy relies on consistency and explanatory power. A theory that unifies previously disconnected phenomena, solves long-standing paradoxes, and reproduces known physics naturally gains credibility even before direct confirmation arrives. Inflation followed this path. So did general relativity before the first measurements confirming its predictions. Some theories about what lies beyond the observable universe may eventually transition from speculation into accepted science through this gradual accumulation of indirect support. Still, there may be limits beyond which scientific investigation cannot proceed. Certain regions of reality may remain permanently hidden behind causal barriers or informational horizons. The multiverse, if it exists, may be fundamentally inaccessible. Other quantum branches may remain forever isolated through decoherence. Structures beneath spacetime may operate at scales impossible to probe experimentally. There is no guarantee that every aspect of existence is observable or testable from within our local cosmic environment. This possibility introduces a philosophical tension within cosmology. Science seeks objective descriptions grounded in evidence, yet the structure of the universe may place some truths forever beyond direct verification. Cosmologists are therefore forced into an unusual position. They must carefully distinguish between what is observed, what is inferred, and what is mathematically possible. The observable universe provides data. Theory extends beyond the data. But eventually, theory reaches domains where empirical access may disappear entirely. And yet the effort continues, because even partial understanding transforms our perspective. The realization that the observable universe is not the totality of existence has already changed humanity's conception of reality. The cosmos is larger, older, and stranger than earlier generations imagined. The horizon surrounding us is not an edge, but a limit imposed by light, expansion, and the structure of space-time itself. Beyond that limit lies more universe, perhaps infinitely more, and possibly forms of reality fundamentally unlike anything inside our visible bubble. But another possibility remains, one that approaches the question from an entirely different direction. Instead of asking whether there are more universes beyond our horizon, some physicists and philosophers have begun asking whether the universe we observe is itself artificial, a constructed informational environment generated by deeper processes we do not perceive. If reality emerges from information, mathematics, and computation, then the boundary between physics and simulation becomes increasingly difficult to define. The simulation hypothesis did not originate within mainstream cosmology, but it emerged naturally from several converging trends in physics, computer science, and philosophy. As researchers began describing reality in increasingly informational terms, comparing physical systems to computations and quantum processes to forms of information exchange, a provocative question appeared almost inevitably. If conscious beings eventually develop the ability to simulate entire worlds populated by self-aware observers, how could anyone inside such a simulation determine whether their own universe is fundamental or artificial? The modern version of the argument was formulated most famously by the philosopher Nick Bostrom in the early 2000s. His reasoning was not based on science fiction imagery or hidden digital messages buried in the cosmos. It was a statistical argument rooted in probability. Bostrom proposed that at least one of three possibilities must be true. Either civilizations almost always go extinct before developing advanced computational capabilities, or advanced civilizations lose interest in creating detailed simulations of conscious beings, or simulated observers vastly outnumber biological ones. If the third possibility holds, then, statistically speaking, any randomly selected observer is more likely to exist inside a simulation than within the original physical civilization that created it. The argument is unsettling because it does not require impossible technology in principle. Human civilization has already begun constructing increasingly sophisticated virtual environments. Modern simulations reproduce weather systems, galactic evolution, ecosystems, and aspects of human cognition with growing realism. Artificial intelligence systems can now generate convincing images, voices, and interactive environments in real time. If technological development continues for thousands or millions of years, the computational resources available to advanced civilizations could become almost unimaginable compared to present standards. A sufficiently advanced civilization might possess the ability to simulate entire planetary histories or even complete universes containing billions of conscious entities. From the perspective of observers inside such a simulation, the environment would appear completely real because all observations, memories, and physical measurements would emerge from the simulation itself. There would be no external vantage point available from within the system. At first glance, the idea sounds less like physics and more like philosophy, but some researchers have explored whether a simulated universe might produce observable signatures. If reality is computational, perhaps the underlying architecture imposes constraints similar to those found in computer systems. Space and time might possess finite resolution. High-energy particles might reveal subtle grid-like effects. Certain physical constants might reflect optimization constraints imposed by limited computational resources. Some speculative studies have examined whether the behavior of ultra-high-energy cosmic rays could reveal evidence of underlying discretization in spacetime. Others have suggested that quantum uncertainty itself resembles computational compression, where reality only resolves definite states when measurements occur, analogous to a rendering engine generating detail only when needed. These ideas remain highly speculative, and no convincing evidence of simulation has ever been found. But the fact that serious physicists occasionally discuss such possibilities reflects how radically our understanding of reality has evolved. The simulation hypothesis intersects in unexpected ways with many of the concepts already explored. If spacetime emerges from informational processes, then the distinction between physical law and computation becomes less rigid. Quantum mechanics already describes reality probabilistically rather than deterministically. The holographic principle suggests information may be more fundamental than spatial geometry. Black hole thermodynamics connects entropy, information, and gravity in ways that remain only partially understood. The universe increasingly resembles an informational system governed by mathematical rules. Yet the simulation idea also faces major criticisms. One problem is explanatory regression. If our universe is simulated, then the civilization running the simulation must exist within some larger reality governed by its own laws. The question of ultimate existence is merely pushed back one level rather than answered. Another problem concerns computational feasibility. Simulating an entire universe down to quantum precision may require computational resources comparable to the universe itself, potentially making the concept impractical even for highly advanced civilizations. There is also the issue of testability. A simulation advanced enough to reproduce conscious observers convincingly could likely conceal its own artificial nature completely. Any apparent evidence might itself be part of the simulation. This makes the hypothesis difficult, perhaps impossible, to falsify scientifically. Some physicists therefore regard it as philosophically interesting, but scientifically unproductive. Still, the simulation hypothesis performs an important conceptual function. It forces us to confront the possibility that observed reality may not correspond directly to ultimate reality. Human beings naturally assume that the world perceived through experience represents the deepest layer of existence. But physics has repeatedly undermined that intuition. Matter turned out to consist mostly of empty space. Time proved relative rather than absolute. Quantum objects ceased behaving like ordinary objects altogether. The observable universe itself became merely a local horizon within something larger. The simulation argument extends this pattern further. What if the physical laws we discover are local rules governing our observable environment rather than fundamental truths about ultimate reality? What if the constants of nature are parameters chosen by deeper processes? What if our entire cosmos is one layer within a nested hierarchy of realities? Whether or not the simulation idea is correct, it highlights an important feature of modern cosmology. The deeper science probes the structure of reality, the more the distinction between physics, mathematics, information, and philosophy begins to blur. Questions that once belonged purely to metaphysics increasingly overlap with serious theoretical physics. The boundary between scientific inference and philosophical speculation becomes difficult to define when discussing regions forever beyond direct observation. This becomes especially apparent when considering infinity itself. Many cosmological models imply not merely a very large universe, but an actually infinite one. Inflationary cosmology, flat spatial geometry, and eternal expansion all point naturally toward infinite spatial extent. Yet, infinity introduces consequences so counterintuitive that even experienced physicists struggle to interpret them coherently. In an infinite universe containing matter distributed roughly uniformly, every physically possible arrangement of particles must eventually repeat somewhere. The number of possible configurations within any finite region, while staggeringly large, is still finite, because quantum mechanics limits the amount of information that can occupy a finite volume. Given infinite space, those configurations recur endlessly. This means there may exist regions beyond our observable horizon where every possible variation of history unfolds. Somewhere, according to this reasoning, there are galaxies identical to ours down to the smallest detail. There are planets identical to Earth. There are observers identical to us having identical conversations. Further away still, there are regions differing by only tiny variations. A single change decision, a slightly altered evolutionary path, a civilization that developed earlier or never emerged at all. This conclusion does not arise from fantasy, but from straightforward statistical reasoning applied to infinite space. If the universe is truly infinite and sufficiently uniform, repetition becomes unavoidable. The observable universe becomes one finite arrangement among infinitely many recurring patterns scattered across endless cosmic distances. The scales involved are so enormous that ordinary language begins to fail. Estimates based on quantum informational limits suggest that an exact duplicate of our observable universe, if infinite space exists, would likely be separated from us by distances so immense that writing them conventionally would fill pages with digits. No signal could ever cross such gulfs. The duplicates, if they exist, are permanently inaccessible. There is something psychologically strange about this implication. Human identity has historically been tied to uniqueness, yet, in an infinite cosmos, uniqueness may disappear entirely. Every physically possible observer may exist infinitely many times. Every possible history compatible with physical law may unfold somewhere. Reality becomes not a single narrative, but an immense statistical structure exploring every allowed configuration. Some physicists resist these conclusions, arguing that actual infinities may not exist physically even if they appear mathematically convenient. Others accept infinity, but question whether repeated regions should be considered genuinely identical if they remain forever causally disconnected. The debate reflects a deeper issue within cosmology. Mathematics often extends naturally into domains far beyond observation, but determining whether those domains correspond to physical reality remains difficult. Infinity also produces paradoxes. In an infinite multiverse where every possible observer exists infinitely many times, how should probabilities be defined? How do you calculate the likelihood of any event when every event occurs endlessly? This is known as the measure problem, and it remains one of the central unresolved issues in eternal inflation theory. Different methods of assigning probabilities produce different predictions, and no consensus solution currently exists. The measure problem illustrates a recurring challenge in theories extending beyond the observable universe. Once reality becomes sufficiently vast, ordinary reasoning about probability and typicality begins to break down. Concepts that function well within finite systems behave strangely when extended to infinite ensembles. Cosmology, at its deepest levels, increasingly confronts the limitations of human intuition and even of standard mathematical interpretation. Yet despite these difficulties, the central conclusion remains remarkably robust across many different theories. The observable universe is almost certainly not the entirety of existence. Whether through inflationary expansion, quantum branching, higher dimensional structures, emergent spacetime, or infinite geometry, modern physics consistently points toward realities extending beyond our visible horizon. The exact nature of those realities remains uncertain. Some may resemble our own cosmos closely. Others may obey different physical laws entirely. Some may be inaccessible because of cosmic expansion. Others because of quantum decoherence or dimensional separation. Some possibilities may never become testable experimentally, but the cumulative direction of modern cosmology is unmistakable. The visible universe is local, not total, and this realization changes the meaning of the night sky itself. When we look outward through telescopes, we are not seeing the full universe. We are seeing a finite shell of ancient light surrounding our position in space and time. Beyond that shell lies vastly more reality, perhaps infinitely more, stretching into regions no human being will ever observe directly. But there is one final boundary even deeper than the cosmological horizon, a boundary not merely of distance or observation, but of explanation itself. Every cosmological model, no matter how large or sophisticated, eventually confronts the same question. Why does any of this exist at all? Why is there a universe, or multiverse, or mathematical structure rather than nothing? And it is here, at the edge of explanation, that physics approaches perhaps its greatest limit. The question of why anything exists at all is older than science itself. Ancient philosophers debated whether existence required a cause, whether the universe had always existed, or whether reality emerged from some deeper principle beyond human understanding. Modern cosmology has transformed many ancient mysteries into measurable scientific problems, tracing cosmic expansion backward toward an early hot, dense state and uncovering the physical processes that shaped galaxies, stars, and planets. Yet the deeper question persists. Even if we explain how the observable universe evolved, why did the laws permitting such evolution exist in the first place? For a long time, many scientists hoped the universe might ultimately be fully self-explanatory. Perhaps all physical laws could be derived from a single elegant mathematical framework. Perhaps a final theory would reveal that reality could exist in only one logically consistent way. In such a picture, the existence of the universe would cease to appear contingent. The laws of physics would not be arbitrary choices among alternatives, but necessary consequences of mathematical consistency itself. This hope motivated generations of physicists searching for unified theories. Einstein spent the later part of his life pursuing a single framework capable of combining gravity and electromagnetism. Later researchers expanded the effort, attempting to unite all fundamental forces into one coherent mathematical structure. String theory became one of the most ambitious attempts, proposing that all particles and interactions emerge from tiny vibrating strings embedded within higher dimensional geometries. Loop quantum gravity pursued a different route, seeking to quantize spacetime itself. Other approaches introduced causal sets, emergent geometries, or algebraic structures underlying physical law. Yet, despite decades of work, no final theory has emerged. More importantly, some developments have complicated the original dream of uniqueness. Instead of revealing one inevitable set of physical laws, modern theoretical physics increasingly suggests a vast landscape of possible laws and configurations. String theory, for example, appears capable of producing an enormous number of mathematically consistent universes, each with different constants and particle properties. Inflationary cosmology may generate regions realizing many of these possibilities physically. The universe we observe could therefore be only one local realization within a much larger space of possibilities. This shifts the explanatory problem rather than solving it. Why do we inhabit this particular region with these particular laws? One proposed answer is anthropic selection. Observers naturally find themselves in regions compatible with the existence of observers. Universes incapable of producing stable matter, long-lived stars, or chemistry simply contain nobody to ask questions about them. In this framework, the apparent fine-tuning of physical constants no longer requires a deeper mechanism. It reflects a selection effect operating across a vast multiverse of possibilities. The fine-tuning problem itself is striking. Several constants of nature appear delicately balanced within narrow ranges, compatible with complex structure. If the strong nuclear force were slightly weaker, atomic nuclei would not hold together efficiently. If it were slightly stronger, stellar processes would behave differently enough to disrupt element formation. If the cosmological constant were significantly larger, accelerating expansion would prevent galaxies from forming. If gravity differed substantially in strength, stars might burn too quickly or fail to ignite altogether. Physicists have debated for decades whether this apparent fine-tuning demands explanation. Some believe a deeper theory will eventually reveal why the constants must possess their observed values. Others argue that a multiverse naturally explains the issue statistically. In an enormous ensemble of universes with varying parameters, at least a few regions will accidentally possess conditions compatible with life. Observers inevitably emerge in those rare regions, but anthropic reasoning remains controversial. Some scientists regard it as a legitimate explanatory tool. Others see it as dangerously close to abandoning predictive science altogether. A theory capable of accommodating almost any observation risks losing explanatory power because it becomes difficult to falsify. The debate reflects a deeper tension within cosmology between explanatory ambition and empirical constraint. The question becomes even stranger when considering quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole. In ordinary quantum mechanics, systems evolve probabilistically within a pre-existing space-time background. But when the entire universe is treated quantum mechanically, there is no external observer and no external clock. The universe contains everything physical. This forces physicists to rethink concepts like time, causality, and observation at the deepest level. Some approaches to quantum cosmology suggest that the universe could arise spontaneously from quantum processes without requiring a classical cause. In certain models, quantum fluctuations allow space-time itself to emerge from states lacking classical geometry altogether. The universe, in this view, resembles a quantum tunneling event where existence appears probabilistically from a deeper quantum framework. Physicists Alexander Vilenkin and others developed models in which universes can nucleate spontaneously from quantum vacuum states. Importantly, the quantum vacuum is not empty in the ordinary sense. It is a fluctuating structure governed by physical laws and quantum fields. Virtual particles constantly appear and disappear within it. Under certain conditions, entire expanding spacetimes may emerge through related processes. This idea is sometimes summarized loosely by saying the universe came from nothing, but the phrase is misleading. The quantum vacuum described by physics is not philosophical nothingness. It possesses structure, mathematical rules, and physical properties. The deeper question remains unanswered. Why does the quantum framework itself exist? Stephen Hawking and James Hartle proposed another influential model known as the no-boundary proposal. In their framework, the early universe does not possess a singular beginning in the ordinary sense. Near the earliest stages, time behaves more like a spatial dimension, smoothing out the boundary where classical intuition expects a beginning. The universe becomes finite, but without an initial edge, analogous to how the surface of Earth is finite, yet lacks a sharp boundary at its poles. These models attempt to remove the need for a singular starting point where physics breaks down completely. But they do not eliminate the deeper mystery of existence itself. They describe how space-time may behave under extreme conditions. They do not explain why there's a mathematical framework capable of generating space-time at all. Some philosophers and physicists have therefore proposed that mathematics itself may be the ultimate foundation of reality. The physicist Max Tegmark, for example, argued that all mathematically consistent structures exist physically in some sense. According to this view, our universe exists because it is mathematically possible. Physical existence and mathematical existence become equivalent. This idea, sometimes called the mathematical universe hypothesis, is one of the most radical extensions of modern cosmology. If correct, every consistent mathematical structure corresponds to a real universe. Reality becomes an immense hierarchy of mathematical possibilities, with our observable cosmos representing one particular structure among infinitely many. The hypothesis attempts to answer why the universe obeys mathematics so effectively. Rather than mathematics describing reality externally, reality simply is mathematics. Conscious observers emerge within certain mathematical structures capable of supporting complexity and self-awareness. Critics argue that the proposal stretches the meaning of existence beyond usefulness. Mathematical consistency alone may not guarantee physical reality. Others point out that the hypothesis struggles to explain why conscious experience arises within certain structures and not others. Yet even its critics acknowledge the remarkable effectiveness of mathematics in describing the physical world remains one of the deepest mysteries in science. There's another possibility, less satisfying scientifically, but difficult to dismiss philosophically. Reality may simply exist without deeper explanation. The universe, multiverse, or mathematical framework may represent a brute fact requiring no external cause. Human beings naturally seek explanations because explanation is central to cognition and survival. But nature may not guarantee that every question possesses an answer, accessible to human reasoning. This possibility is uncomfortable because it imposes a limit on understanding itself. Science has achieved extraordinary explanatory success by assuming phenomena possess discoverable causes and lawful structures. Yet the chain of explanation may not extend infinitely. At some level, existence itself may resist further reduction. There are practical limits as well. Human civilization occupies a tiny region of space and time. The observable universe contains finite information accessible to us. Even with perfect technology, there may be questions the universe simply does not contain enough observable data to answer conclusively. Theories extending far beyond the cosmological horizon may remain permanently underdetermined by evidence. And yet, despite these limitations, cosmology has already revealed something extraordinary. The universe, visible to us, is not the whole of reality. The stars overhead, the galaxies mapped by telescopes, even the cosmic microwave background itself, all represent a local perspective constrained by finite light speed, cosmic expansion, and the structure of space-time. Beyond the observable horizon lies more universe. Beyond that may lie inflationary regions forever disconnected from ours. Beyond those may exist branching quantum realities, higher dimensional structures, or entirely different physical domains. Human beings evolved on a small planet orbiting an ordinary star inside one galaxy among trillions. Yet within a few centuries of scientific inquiry, we discovered that even the observable universe is only a fragment of something larger. The boundaries surrounding us are not edges of existence, but limits of observation. There is a quiet irony in this. The more precisely cosmology measures reality, the larger the unknown becomes. Every advance expands the horizon of unanswered questions. Telescopes revealed galaxies beyond the Milky Way. Cosmology revealed the observable universe beyond those galaxies. Inflation suggested immense regions beyond the observable horizon. Quantum theory hinted at branching realities beyond classical spacetime. The search for fundamental physics now points toward structures beyond space and time themselves. The observable universe, once imagined as totality, has steadily diminished in relative importance. It is not the center of reality. It is not even the majority of reality. It is a local bubble of accessible information suspended within something far larger and perhaps fundamentally inaccessible. And still, the light continues arriving. Photons that began traveling before Earth existed continue crossing expanding space toward our detectors. Every telescope image captures ancient signals from regions already altered beyond recognition. The night sky is not merely a view into distance, but into time itself, a layered archive of cosmic history approaching us at light speed across an expanding sea of space-time. Somewhere beyond that horizon, galaxies shine whose light will never reach Earth. Entire civilizations, if they exist, remain forever causally isolated from ours. Quantum branches unfold inaccessible through decoherence. Inflationary regions expand beyond communication. The cosmos continuously exceeds the boundaries of perception. What lies beyond the observable universe, then, is not a single answer, but an expanding hierarchy of possibilities. More galaxies, more spacetime, other inflationary domains, quantum branches, higher dimensions, mathematical structures, perhaps realities operating under laws completely unlike our own, perhaps limits beyond which human concepts cease functioning altogether. The observable universe is not a wall surrounding existence, it is a moving horizon surrounding knowledge. And beyond it, reality continues. Whether humanity will ever move meaningfully beyond that horizon is another question entirely. The physical limits imposed by relativity and cosmic expansion place severe restrictions on exploration. Popular imagination often assumes that sufficiently advanced technology will eventually overcome any barrier, but the universe is not obligated to permit unlimited access. Some boundaries appear deeply embedded within the structure of reality itself. Interstellar travel alone presents enormous difficulties. The nearest star system beyond the Sun lies more than 4 light-years away. With present technology, reaching it would require tens of thousands of years. Even hypothetical propulsion systems far beyond current engineering capabilities struggle against the immense energy requirements imposed by relativistic motion. As velocity approaches the speed of light, the energy needed for further acceleration increases dramatically. Reaching even a substantial fraction of light speed would demand technological capacities far beyond anything civilization currently possesses. And yet, interstellar distances are small compared to cosmological ones. The Milky Way spans roughly 100,000 light-years. The nearest major galaxy, Andromeda, lies 2.5 million light-years away. The observable universe stretches across 93 billion light-years of present-day distance. Even if a civilization developed spacecraft capable of traveling extremely close to light speed, expansion itself would still prevent access to most of the cosmos. Regions beyond the cosmic event horizon are receding too rapidly for any future signal or traveler ever to reach them. This means the observable universe is not merely difficult to traverse. Much of it is fundamentally unreachable even in principle. The accelerating expansion driven by dark energy gradually isolates gravitationally unbound regions from one another. Civilizations arising in distant galaxies may remain forever disconnected, separated not by engineering limitations, but by the geometry of space-time itself. There are speculative ideas for bypassing some of these constraints. General relativity permits unusual space-time geometries under certain conditions. Wormholes, hypothetical tunnels connecting distant regions of space-time, appear mathematically possible within Einstein's equations. If stable traversable wormholes could exist, they might allow shortcuts between otherwise unreachable regions. Similarly, concepts like warp drives propose manipulating space-time itself, contracting space ahead of a spacecraft and expanding it behind. But these ideas encounter major obstacles. Traversable wormholes appear to require exotic forms of negative energy not known to exist in sufficient quantities. Warp drive geometries likewise demand conditions far beyond anything experimentally demonstrated. Quantum effects may destabilize such structures before they become usable. The mathematics permits intriguing possibilities, but nature may forbid their realization physically. Even communication faces limits. Any message transmitted across intergalactic distances requires immense spans of time to arrive. A civilization receiving a signal from another galaxy would encounter information millions or billions of years old. By the time a reply returned, if one ever could, entire species might have vanished. Cosmic communication unfolds on timescales so large that meaningful interaction becomes nearly impossible. This introduces a strange loneliness into cosmology. The universe may contain immense numbers of civilizations scattered across countless galaxies, perhaps even across inflationary regions beyond our horizon. Yet, the structure of space-time may isolate most of them permanently. Reality could be full of intelligence while remaining effectively silent. The Fermi paradox emerges naturally from this tension. Given the enormous age and scale of the universe, why has no clear evidence of extraterrestrial civilization appeared? Some solutions propose that intelligent life is extraordinarily rare. Others suggest technological civilizations tend to destroy themselves before achieving large-scale expansion. Still, others point out that the observable universe is simply too vast for easy detection or contact. Cosmic expansion deepens the paradox further. Even if advanced civilizations arise frequently, accelerating expansion may trap them within local regions before they can spread significantly across intergalactic space. The universe itself may prevent the emergence of galaxy-spanning civilizations, except under extremely specific conditions. There is also the issue of time. Human civilization has existed for only a tiny fraction of cosmic history. Modern science occupies mere centuries within a universe nearly 14 billion years old. Intelligent observers may appear and disappear across cosmic epochs without overlapping temporally. Entire technological civilizations could rise and vanish before their light ever reaches one another. The future evolution of the cosmos will only intensify this isolation. As dark energy drives continued acceleration, distant galaxies will gradually disappear beyond the event horizon. The observable universe accessible to future observers will shrink effectively over time. Eventually, only the remnants of the local gravitationally bound group of galaxies will remain visible. Future astronomers living trillions of years from now may inhabit a profoundly different observational environment. The cosmic microwave background will have stretched into wavelengths too large to detect. Evidence of the Big Bang may vanish observationally. Distant galaxies will disappear beyond the horizon. Those observers may conclude, incorrectly, that the universe consists only of their isolated galactic system surrounded by emptiness. This possibility is remarkable because it means cosmology itself depends on historical timing. Humanity happens to exist during an epoch when the evidence necessary to reconstruct cosmic history remains accessible. We can observe expansion, detect the microwave background, and map distant galaxies. Earlier in cosmic history, the universe was too hot and chaotic for intelligent observers. Later, much of the evidence will fade permanently beyond reach. In that sense, the present era is scientifically privileged. The universe has evolved long enough to produce stars, planets, heavy elements, and conscious life, yet not so long that cosmic expansion has erased the evidence of larger structure. We occupy a narrow observational window during which the broader cosmos can still be reconstructed. There is something deeply humbling about this realization. Human beings often imagine themselves arriving late to cosmic understanding, living in an ordinary era within an ancient universe. Yet from the standpoint of observational cosmology, this may be one of the best possible moments to study reality. The horizon has not yet closed completely. At the same time, many mysteries remain unresolved. Dark matter, which outweighs ordinary matter throughout the universe, has never been directly identified. Dark energy, driving cosmic acceleration, remains deeply mysterious. Quantum gravity continues to resist complete formulation. Inflation explains many observations, but lacks definitive confirmation of its underlying mechanism. The ultimate structure of reality remains uncertain. And perhaps uncertainty itself is unavoidable. Scientific progress often creates the impression that knowledge advances steadily toward complete understanding. But cosmology increasingly suggests that some aspects of reality may remain permanently hidden. Horizons, causal barriers, quantum limits, and finite observational access all constrain what can be known from within a single observable region. This does not diminish science. If anything, it reveals the extraordinary reach of human reasoning. A species confined to one small planet has inferred the existence of galaxies billions of light years away, reconstructed the thermal history of the early universe, measured space-time curvature, detected black holes, and uncovered quantum laws governing matter itself. The fact that some boundaries remain inaccessible does not negate these achievements. It defines the frontier where knowledge transitions into informed speculation. The observable universe therefore occupies a peculiar position. It is both unimaginably vast and profoundly limited. Vast enough to contain trillions of galaxies and more stars than grains of sand on Earth. Limited because it represents only the portion of reality whose light has had time to arrive since the beginning of cosmic expansion. Beyond that horizon, the universe almost certainly continues. The evidence for continuation is overwhelming. Space does not appear to terminate abruptly at the edge of observation. Expansion does not suggest a boundary. Inflation points naturally toward enormous unseen regions. Flat geometry implies potentially infinite extent. Every successful cosmological model extends beyond the visible bubble rather than ending at it. And so, the horizon surrounding us is best understood not as an edge but as a perspective. It marks the limit of what can currently influence us and what we can currently observe. Another observer, billions of light years away, inhabits a different observable universe centered on their own position, with horizons overlapping ours partially while extending into regions forever inaccessible to us. Reality, in this sense, has no universal center. Every observer sees themselves surrounded by a cosmic horizon. Every civilization inhabits its own sphere of observable history, embedded within a larger structure none can fully perceive. The universe appears constructed not around privileged locations, but around local perspectives constrained by light and time. This idea subtly transforms humanity's place within the cosmos. Earlier worldviews placed Earth at the center of existence. Modern cosmology removed that centrality completely. But the observable universe introduces a different kind of centrality. Each observer occupies the center of their own visible horizon, not because they are cosmically important, but because information propagates finitely through space-time. The result is a universe simultaneously objective and deeply perspectival. Physical laws appear universal, yet every observer accesses only a local fragment of the total structure. No being, no matter how advanced, may ever observe the whole. And perhaps that is the final lesson hidden beyond the observable universe. Reality exceeds complete description, not because science has failed, but because existence itself may be fundamentally larger than any single perspective can contain.